Hello, I'm Anthony Pepitone, and this is Lab 3, Experiments with a Black Hole. The main purpose of this lab is to find the mass of a black hole utilizing the star's orbit around it, and the second part of this lab, we will be determining the initial velocity a ship must have to make it off the planet and go around the black hole without crashing. A brief preview of these results shows that the mass of the black hole is about 1.52 times 10 to the 34th kilograms, and the initial velocity of the ship is around -1 times 10 to the 7th and 1 times 10 to the 7th meters per second. A couple of the main principles and ideas that we will be using for this lab are the universal law of gravitation, also known as Fg, is equal to -g times the masses over r squared times r hat. Along with this, we have Newton's second law and the momentum principle, which are F net is equal to ma, or F net is equal to dp over dt. We also must take into account F net parallel, which is mv squared over r, and F net perpendicular, which describes the change in direction, which is perpendicular to the F net parallel. These two forces of F net parallel and F net perpendicular add together to give us the total force. Along with these two, we need to keep using our velocity update and our position update formulas to determine the movement within this experiment. And finally, we're going to be assuming that the only forces acting on the objects are gravity due to the fact that we are in space. The system and surroundings for the first part of this experiment are going to be the system as the black hole and the surroundings as the star, with the initial conditions that the star's mass is 2 times 10 to the 30th kilograms, and delta t is going to be 86,400 seconds, or 1 day. For the coding for the first part of this experiment, we have on the left side the initial conditions. On the right side, the top arrow shows that we have dp dt as the change in momentum over change in time. Under that, we have the terms to define F parallel in the momentum and placing it as our force. The next arrow takes the total dp dt and subtracts the parallel in order to get the perpendicular component. Our last arrow shows the universal law of gravitation, changing some of it in order to find the mass of the black hole. The results of this code give us that the mass of the black hole is 1.52 times 10 to the 34th. The magnitude of F, or the forces, is 9.57 times 10 to the 28th. Along with this, the components of parallel is 3 times 10 to the 27th, and the magnitude of F net perpendicular is 9 times 10 to the 28th. The system for the second part of this experiment is the spaceship, and the surroundings are both the black hole and the star. Along with this, we will use our mass of the black hole, which we found to be 1.52 times 10 to the 34th. Along with this, we have the mass of the planet as 9 times 10 to the 28th, and the mass of the ship as 7 times 10 to the 10th. In order to get the initial conditions for the planet, we have the speed as the square root of gravity times the mass of the black hole over the magnitude of the planet's position, and our velocity to be the vector of 0 times the planet's speed and 0. In order to calculate the motion for all of the moving objects, we are going to be rearranging our universal law of gravitation in order to get the gravity's effect on both the planet and the ship. On the first arrow, we have the forces of gravity acting on the planet from both the black hole and the ship. Next, we take the gravity forces on the ship from the black hole and the planet, still utilizing this universal law of gravitation. Lastly, we update the formulas in order to make the motion happen. We see that the planet velocity is equal to the planet's velocity initial plus F net on the planet over m times delta t, and the planet's position is equal to the planet position plus planet velocity times delta t, and we do the same thing for the ship's velocity and the ship's position. After guessing and checking with the code, we find that the ship's initial velocity in the x direction is -1.00918 times 10 to the 7th, and in the y component is 1.00917 times 10 to the 7th. While there is no real-life data to compare the model to, the two models are similar in that the planet follows the same orbit. However, they are different in that the first one is aiming to measure the perpendicular and parallel components of the planet's orbit, whereas the second one aims to measure an entirely new system, being the ship. Some possible errors would be in that the first part, I did not let the program run for enough time or did not have a high enough t interval, therefore changing the average mass that we used to find the mass of the black hole. In the second part, we could have used different rounding, especially with the large numbers, resulting in different decimal points. What does it mean? The net force is the same rate of change as momentum. Therefore, components of perpendicular and parallel will align with each other. This is why we can make calculations based off the object's motion. The force and its components are able to determine the motion and vice versa. That is why we can use the motion to determine the force due to the rate of change. In the second part, if we wanted to orbit the black hole rather than just passing by it, but not crash into the planet, we would need to have a similar velocity to the planet, but changing the y component. If we have the similar velocity of the planet, we would be able to orbit just as the planet does. But by slightly changing the y component, we would have a slightly different orbit and therefore avoid crashing into the planet.